Humans have built cities, composed symphonies, landed machines on distant planets, and taught themselves to laugh at things that scare them. Every single one of those achievements traces back to the same source. Not muscle, not size, not speed. Something far less visible and far more powerful, the capacity to think, adapt, and solve. We call it intelligence, but the moment you try to pin down exactly what that word means, it starts to slip through your fingers. Ask 10 scientists, and you will get 10 different answers. Some focus on the ability to learn. Others point to memory, or creativity, or problem-solving. Some argue it requires self-awareness. Others say it shows up long before awareness enters the picture. What most agree on is this: intelligence, in its most fundamental form, is about survival. It is a set of abilities that help living things navigate a world that is constantly changing, constantly threatening, and never quite the same twice. Think about what surviving actually requires. You need to find food before you starve. You need to recognize danger before it reaches you. You need to compete for mates, territory, and resources against others who want the same things. And you need to do all of this in environments that shift with the seasons, the weather, and the behavior of everything else alive around you. Intelligence is what lets living things do more than simply react. It lets them anticipate, plan, adapt, and sometimes completely reinvent their approach when the first one fails. But intelligence is not one tool. It is more like a collection of tools that living things carry in different combinations, depending on what their lives actually demand of them. Some creatures carry a small and highly specialized set. Others carry a sprawling, messy toolkit capable of tackling almost anything. Understanding intelligence means looking at those tools one by one and asking what each one actually does. The most foundational tool is perception. Before anything else can happen, a living thing needs information about the world around it. This is what senses are for: vision, hearing, smell, touch, taste, pressure, temperature, magnetic fields. Different creatures have evolved radically different sensory systems depending on what information matters most for their survival. A shark detects electrical fields produced by the muscle movements of prey buried under sand. A dog constructs a detailed portrait of a place from scent alone. A bat navigates complete darkness by bouncing sound off surfaces and reading the echoes. Perception is not just receiving signals. It is already a form of processing, already a kind of intelligence, because what matters is not the raw data, but what the organism does with it. Alongside perception, every living thing also needs to monitor its own internal state. Hunger, thirst, pain, exhaustion, reproductive readiness, these internal signals shape behavior just as powerfully as anything happening in the outside world. Without them, an animal cannot prioritize. It cannot know whether to hunt or rest, whether to fight or flee, whether to eat or continue searching for something better. This self-monitoring is a quietly essential piece of the intelligence puzzle, easy to overlook because it is invisible, but foundational to everything built on top of it. Information becomes dramatically more powerful when it can be stored. This is where memory enters. Memory allows a living thing to carry the past forward into the present, so that each new encounter does not have to be treated as if it is happening for the very first time. A bird that remembers where it buried seeds last autumn does not have to re-explore its entire territory when winter arrives. A dolphin that remembers which feeding strategies worked in which conditions does not have to rediscover that knowledge through trial and error every time. Memory compresses experience into something usable, something that can be retrieved and applied in future moments that resemble past ones. Memory also makes learning possible. Learning is the process of refining behavior over time based on what memory has retained. It is the difference between doing something randomly and doing something deliberately. When a young animal watches its mother hunt and gradually internalizes the pattern of movements involved, that is learning. When a crow tries multiple approaches to extract food from a difficult container, keeping what works and discarding what does not. That is learning. The process requires memory to store what was attempted, perception to evaluate the result, and some kind of mechanism to update behavior accordingly. Together, these three tools, perception, memory, and learning, form the foundation on which all higher intelligence is built. Even with only these basic tools, animals are capable of behavior that surprises us. Cleaner rasa fish, tiny creatures that remove parasites from larger fish, have recently shown signs of recognizing their own reflections in mirrors, a test long thought to require a level of self-awareness that only a handful of large-brained animals could pass. Jumping spiders with brains the size of a poppy seed plan and execute multi-step hunting strategies, sometimes taking routes that temporarily move them further from their prey in order to approach from a better angle. These are not large animals. They are not animals we instinctively credit with sophistication, but they are solving real problems in flexible, non-instinctive ways, and that is worth paying attention to. As brains became more complex over evolutionary time, a new layer of capability emerged. The ability to store not just isolated memories, but interconnected knowledge, cause and effect relationships, patterns, categories, rules about how the world tends to behave. This is sometimes called associative learning, but in its more elaborate forms, it starts to look a great deal like understanding. Ravens, for instance, have been observed caching food and then returning to move it if they noticed another raven watching them hide it. This requires the raven to model what the other raven knows, which means holding a representation of another mind inside its own. That is a remarkably sophisticated cognitive move for any animal. Chimpanzees have been documented using sets of different tools in sequence to solve problems, using one stick to knock down a box, another to open it, and a third to extract the food inside. Each step requires anticipating the next one, which means the chimp is running a kind of mental simulation of the future before committing to action. This is planning in a meaningful sense of the word, not just habit or instinct, but the projection of a desired outcome and the construction of a path toward it. Creativity sits at the furthest edge of this toolkit. It is the ability to recombine existing knowledge in ways that have not been tried before, to find novel solutions to novel problems, to produce something genuinely new. In humans, this expresses itself in art, mathematics, engineering, and humor. In other animals, it shows up in ways that are harder to categorize, but no less striking. A captive orangutan observed the keepers at her facility using a hose and later used a similar object she had access to in the same way, without ever being shown or rewarded for doing so. She had watched, inferred the principle behind the behavior, and transferred it to a new context. That transfer, from observation to abstraction to application, is exactly what creativity requires. What determines which tools any given species develops is not raw intelligence potential, but ecological pressure. The problems a species needs to solve shape the cognitive equipment it evolves to carry. Wolves that hunt cooperatively in packs develop sophisticated social coordination abilities. Octopuses that hunt alone in complex reef environments develop extraordinary individual problem-solving skills and physical dexterity. Neither is more intelligent in any absolute sense. Each is precisely as intelligent as its situation has required it to become, equipped with exactly the tools that give it an edge in the environment it actually lives in. Humans are unusual, not because we possess intelligence, but because of how extreme and how broad our version of it became. The range of problems we can tackle, the depth of abstraction we can reach, the timescales we can think across. These push well beyond anything evolution seems to have strictly required of us. And then we added something that may be the most powerful cognitive tool of all: the ability to pool our intelligence across individuals and across generations. Language, writing, teaching, institutions, science, these are not just cultural achievements. They are cognitive technologies that effectively multiplied the problem-solving capacity of every individual by connecting them to every other individual who ever thought carefully about the same problems. That is how a single species went from sharpened stones to space telescopes in what is, by the timescale of life on Earth, barely a moment. Not because any individual human is so much smarter than a raven or a chimpanzee, but because human intelligence found a way to become collective, to store itself outside individual minds, to persist beyond individual lifespans, to accumulate rather than reset with each generation. The toolbox has been built over hundreds of millions of years, piece by piece, shaped by pressure and time and the relentless demands of staying alive. What happens next depends on whether we are wise enough to use it well.